Alright, this is an example problem about using conservation of energy in order to solve a problem that is a lot more complicated if you're trying to use kinematics. So the idea here is that I have some mass, I've drawn it as a block, up some sort of a ramp. And I'm going to, from rest, let go of that box. And it's going to slide down the ramp, and it's going to hit a spring. And of course, the box is going to have gained some kinetic energy from the potential energy it started with, being as the potential equals zero line is at ground level. So needless to say, once it gets to the spring, it will compress the spring. It will put some of its kinetic energy into spring's potential energy. So let's go ahead and pretend that we can go ahead and take a snapshot when at the very instant that the box is stopped by the spring will be compressed some amount. So we're going to pause it right there, and we're going to figure out what the displacement of this spring is going to be. So let's go ahead and say that the spring has some constant k. So, and this is more about the theoretics. I'm not going to do so much numbers because this isn't an actual problem out of your book, but I just want to show the process. And so, remember, we're looking at some starting point where we're going to have some energy initial, and then we're looking at some ending point. And that ending point, I'm going to draw it again, is when the spring is compressed some amount. Well, that's not a good spring. When the spring is compressed some amount, and that amount we're going to call delta x. And so this will be the moment the block has come to rest. So I'll draw the block there. And so this will be our final position. And we'll be able to find the energy at the final position. And using conservation of energy, if no energy is lost to the system, E initial will equal E final. And so that's the next step, is the sum of our initial energies is going to equal the sum of our final energies. And once again, the beauty of energy is that it's scalar, so we don't have to break it into components and do multiple systems of equations. So I told you that the block started at rest. So that's going to mean that V initial equals 0 meters per second. And I also told you that the block ends its path once it's compressed the spring, and the spring has now stopped the block entirely. So that means that our V final is also 0 meters per second. And I think this is important just to write out what you know before you even hop into the problem. And so now we're going to look and say, well, what energy do I have when I start, and what energy do I have when I stop? So it's clear that when I start, if I choose my potential equals 0 line here, I have some gravitational potential energy given to me by the height orthogonal to the potential equals 0 line. Because remember, gravity only acts in this direction, so we're going to gain the vertical displacement of energy is going to be responsible for our gravitational potential. So some initial energy, we definitely have gravitational potential energy. And because I said it starts at rest, we don't really have any initial kinetic energy. We definitely don't have any other kind of energy but gravitational potential here. So this is all the energy we get to start with. Well, now we're going to look. It slides down the ramp. It's gained some kinetic energy. It compresses the spring, but it stops. And that's the snapshot we're looking at. The spring has completely brought the box to a rest when we paused it. Therefore, V final is 0 meters per second. And so, once again, we don't actually have any kinetic energy at the final state. Of course, we have plenty of kinetic energy along the way. But at the beginning and the end, no kinetic energy. But there is some potential energy. Not gravitational, because we're now at the potential equals 0 line. But we talked about this last time. We have some potential energy due to the spring. And that's about it. I can't think of any other energy that's involved in this system. Of course, assuming there's no friction, it's a frictionless surface. So now let's write what we know about gravitational and spring potential energy. Last time we showed that gravitational potential energy is mgh. Height is the vertical displacement. And the spring potential energy is 1/2 k, the spring constant, x squared, where x is the displacement of the spring, or the from where the spring starts to where the spring finishes. Or you could call it delta x, or just x, assuming that, because of course delta x is just x final minus x initial. So if we just assume that the spring's beginning position is 0, then really delta x is just x final. We can just call it x. So that's why we kind of switch back and forth. So this is basically the end of the problem. Like, for example, if we were given the mass of the object, let's say we were given the constant, the spring constant, and let's say that we were given the displacement of the spring from its initial position to when it stops the block. And of course the question here is going to be, at what height did the box start from? Because of course we know G is 9.8, and so this would be a typical conservation of energy problem. You might also see that you know the mass and you know the height and you know the displacement of the spring, but you're asked to figure out what the constant, the spring constant is. So it can really work either way, but the basics of these problems are going to be very similar. And I think what I'll do now is I'll go ahead and talk about the energy lost to friction. So let's go ahead and say, same problem, but let's say that there's a patch on the flat side of things. There's a patch that has friction. We'll say that the friction between the block and it, and of course it'll be moving, so we'll be looking for some coefficient of kinetic friction, or mu sub k. And so what do we know about friction? Well, we know that the force due to friction is equal to the coefficient of friction times the normal force. And so if we're looking at the flat part of this ramp, we know that we would draw a free body diagram and say, well, the mass of the block times gravity is going downwards, and the normal force is going upwards. Because we're flat at this point and the box isn't falling through the floor, we know that the normal force must be equal to mg, because there's no acceleration anymore in the y direction once we flatten out. So of course sum of forces in the y direction equals 0, because it's static in that direction. And we end up with the normal force up minus mg down equals 0. Therefore the normal force equals mg. And we can go back up to our force due to friction equals mu sub k times the normal force, which is mg. Alright, so that's the first step. The next step is we're going to use this idea again, that work is defined as the integral of the f vector dotted with our infinitesimal displacement vector. And so kind of the nifty thing about this is as you'll recall, the friction force doesn't need to necessarily go up to its maximum unless you're pushing at its maximum. But in this case, the friction force is going to point opposite the direction of motion. So it's going to point in this direction the whole time. And if the friction force is proportional to the normal force and the coefficient of friction, that means that the friction force the whole time in that direction is going to be constant. And a constant force means that the force is not a function of our displacement. Therefore, we can pull it out. Work equals F. Now, dr's integral is just r, and cosine the angle between them. Well, another nifty thing about this is that the cosine angle, if we're moving this way, and the force due to friction is going that way, then the angle between the force vector and the displacement vector r is going to be 180 degrees. Cosine of 180 is minus 1. So we find the work is equal to minus the force of friction times r. And of course the force due to friction is mu k times mg, and so the work that the friction has taken out of the system by loss due to heat primarily is going to be minus mu k mg times the distance that it's been displaced through, this distance r. So the beautiful thing about friction is that it is a constant force acting in the opposite direction, and so we don't actually have to integrate it. Now the more general form I think that you would want to know is that the energy lost to the system due to friction is going to equal the force due to friction times the amount of displacement you are in the friction for. And so, for example, in this case, if we want to do this problem again, you would have to draw a free body diagram to get what the normal force is at that point. But if we wanted to do this problem again, the energy, sum of energies we started with initially equals the sum of energies final. So we still start with potential gravitational energy and nothing else. Now here's the tricky part, is that I consider the energy we lost due to heat. So the energy we lost due to heat, I consider that part of the final term. So in other words, the energy I got out of this potential energy is going to equal the force due to friction times that distance r, plus now we have still the potential energy of the spring. And so as you can see, the spring is going to be compressed less now because of the fact that the force due to friction actually took some energy out of the system as heat. You can also notice that if I put work into the system, so in other words, what if I gave this a push? Well, then the work you put into it would go on the initial side of things. So this is no longer a closed system. We're now losing energy to the system and gaining energy from the system. But as long as we account for those energies that we gain and we lose, the conservation of energy will still hold. And so I hope this was helpful. These are more conceptual videos. I will be doing some practice problems soon, and if you have any requests, please let me know. Thanks for watching. I'll see you next time.